Imagine gazing into the depths of space, where planets orbit stars in endless cosmic silence, and asking, what if one of those worlds is alive? NASA's OptiX and TPF projects could reveal secrets hidden in the starlit darkness, alien oceans, towering forests under foreign skies, or maybe, just maybe, cities glowing on a distant world. What will we see when we finally look closer? Are there civilizations awaiting discovery, their own histories, their own mysteries, looking back at us? Could we be on the brink of a cosmic revelation that changes the way we see ourselves forever? What if, out there, countless worlds are teeming with life? Alien skies filled with creatures beyond imagination, landscapes sculpted by beings with technology far more advanced than ours. NASA's next-gen telescopes promise to pierce the cosmic veil and bring these places into view. But here's the question. Are we prepared to discover that we're not the only ones, that perhaps we're just one chapter in a grand universal story? What mysteries, wonders, and even dangers could await us? And when we see them, will we still feel alone in the universe? Imagine our telescopes focusing on a distant star and finding unmistakable signs of life, a strange atmosphere, an otherworldly signal, or perhaps an entire alien ecosystem. What will it feel like to see a living, breathing world so far from home, to know that life took hold in more places than just Earth? These missions could open our eyes to a universe filled with possibilities, but what if those worlds look back? Will they see us as explorers, or as the first contact from beyond their skies? Are we ready for what we might find, or is the universe about to surprise us in ways we never dreamed? The universe is vast, and within it, untold secrets wait for us to uncover. Imagine pointing our instruments toward a distant star and finding not only life, but intelligence, a civilization as old as the stars, living in ways we've yet to imagine. What if they've been waiting for us, or perhaps even watching us? Could the answers to our deepest questions, the origins of life and the purpose of our existence, lie out there, waiting for us to find them? As we stand on the edge of discovery, the cosmos beckons, asking us to take the leap. Are we ready to embrace the unknown? NASA is thinking about going to Mars. Of course, they won't reach Mars before 2030. In the meantime, what else will the astronauts do? You have to build bigger structures if you want to get people to Mars. We must build a vast space infrastructure for commercial, scientific, and defense uses. Maybe astronauts could get better at putting together big space systems. Maybe the agency should have invested in automatically maintaining these massive structures. Our investment in the International Space Station might benefit from additional leverage. Oh, and you can use our fantastic idea for all of that. The Institute's concept, OptiIIX, Optical Testbed and Integration on ISS Experiment, was developed in partnership with 3 NASA research centers. As early as 2015, a lightweight, flexible, segmented mirror assembly and active correction system could be tested in space by the scalable and affordable OptiIIX platform. Its main mirror is 1.5 meters long and comprises 6 fully functional 50-centimeter hexagonal segments. Atom-thin layers of vaporized metal would cover silicon carbide sheets in each segment. To compensate for the jitter and direct the collected starlight to cameras for imaging and wavefront control, it would bounce from the primary mirror to a smaller secondary mirror before returning to a series of tertiary, fast steering and pick-off mirrors. A latticework of lasers beaming across the primary mirror would be used by star trackers and gyroscopes to precisely point the telescope and maintain its ideal figure. Even with the jarring, heavy and noisy astronauts outside the International Space Station, ISS, these technologies would allow optics to deliver accurate images of stars and galaxies. OptiX's design would enable full robotic assembly and maintenance, while its modular components are being transported into orbit, enabling spacewalks by astronauts to upgrade or repair the system as necessary. We are at the limit of what the present paradigm of heavy launch vehicles and restricted folding geometries can do. Mountain eventually reverted to his professional demeanor and said, as he gazed out his office windows past a windowsill containing 5 framed pictures of his family. Under the weak winter sun, the morning fog had boiled away, exposing a desolate scene of bare trees and slack grass. These days, space telescopes are constructed and tested on the ground before being folded and loaded into a rocket. Without larger rockets, it is impossible to have larger telescopes. Because OptiX removes all extreme tolerances, it could start a scale-invariant process for building ever larger space telescopes. After all, we don't build and test a telescope in a large basement before bringing it to the top of a mountain, do we? No, of course not. We put it together piece by piece on the mountaintop, hoping to align its parts later. Thanks to technological ideas like active optics, you can assemble, align, and upgrade your telescope in space, where it belongs. Imagine your telescope assembled and run by robots, astronauts, or a mix. You continue. You could reach almost infinity with your telescope. I questioned Mountain about the likelihood that this vision would materialize. He dragged a hand over his jaw, making a sound like dry, wind-blown leaves, and furrowed his brow. Finally, he said, Americans could well choose to further divert from space science. In fact, we're spending a lot of federal money. And he seemed to be addressing his spectral reflection in the glass window pane. That money doesn't always come back if it goes missing. Since it aligns with other priorities, I'm not necessarily against it. However, you can imagine the abrupt shift. We might soon lose a large number of the skills we have learned. Nonetheless, it can be argued that science and technology, of which space science is a part, has supported this country and will continue to do so as other economies, including those of China, India, Europe, and others, expand. Whether our current situation results from a natural evolution or is merely a fortunate occurrence. According to Mountain, the heyday of Hubble and the other major observatories was a fortunate anomaly that resulted from economic and geopolitical factors, just as much as from advancements in science and technology. Its origins may lie in the pivotal moments of the Cold War, the space race, and the baby boom in the second half of the 20th century, to create for themselves an almost mythical dream time, a dazzling period in which the limits of technological capability slipped beyond the everyday world of Earth, and the horizons of the scientific discovery reached the edge of the known universe. Astronomers had taken advantage of that improbable convergence of what kind of space telescope would be required. Their calculations were sobering. A single mirror, or filled aperture, at least 5,000 kilometers, 3,000 miles, in diameter, would be needed to create an optical wavelength image of an Earth twin orbiting one of the Sun's closest neighbors. The size of that mirror is similar to the size of the continental United States. If humans didn't suddenly develop the technology to turn massive asteroids into remarkably smooth, polished mirrors. These enormous holes would seem inaccessible forever. Even with the construction of a huge mirror, it would still be a difficult technical task to suppress the 10 billion to 1 glare of starlight. Luckily, the laws of physics provided a single solution to both issues. Light behaves like a particle when it is absorbed by the material of a detector, reflected from the atmosphere of a planet, or released from the surface of a star. However, it behaves similarly to a wave hitting a telescope's mirrors or moving through interstellar space. Instead of photons pinging against raindrops that resemble mirrors, imagine a continuous wave front of light striking and moving simultaneously across every square centimeter of a mirror's surface. A clever astronomer can use the wave-like nature of light to create a single image with a 10-meter aperture resolution by placing two 1-meter mirrors at a 10-meter baseline apart. Any number of connected smaller mirrors can receive the same amount of light wave fronts from a distant source, like a star, as if they were a single large aperture. By putting a 1-meter mirror in Los Angeles and another in New York, then connecting and synchronizing them with a computer-controlled beam combiner, we can create an interferometric array with a baseline of 5,000 kilometers and the resolution of a continent-size mirror. The array's light-gathering capacity would still be on par with those 2-meter-size mirrors, but its synchronization would be hampered by the Earth's rotation, curvature, and surrounding atmosphere. Consequently, collecting enough photons to create a single high-resolution image of an exoplanet would be impossible. However, an interferometer could look into deep space day or night because it would be above the atmosphere. It could be made infinitely large, devoid of gravity and planetary curvature, and fitted with an arbitrary number of individual mirrors to increase sensitivity and a baseline of any length to improve resolution. Furthermore, they could align the light waves by recombining the various waves of light that each mirror collected. This would cause the crests of the wave troughs of one beam to precisely overlap with the crests of another beam, causing them to destroy and splash against each other like out-of-phase ripples on the surface of a pond. Bands in the finished picture. A star's brilliant light would be cancelled out by the shadow's darkness, exposing the faint twinkle of neighboring planets. An interferometric array was the best way to get a blue marble image of any exoplanet, aside from using the sun as a gravitational lens. To create a mission best suited for observing in the infrared, where the star-planet contrast is only 10 million rather than 10 billion in the optical, Elachi and his colleagues seized upon the interferometer concept for a TPF. To create a 75-meter baseline, the mission would use 4 1.5-meter cryogenically cooled mirrors on a linear boom. Since less dust is left over from the solar system's formation to scatter and contaminate the weak light from nearby stars, this baseline would function outside Jupiter's orbit. If the mission operated closer to Earth, each mirror would have to be doubled to 3 meters to accommodate the higher density of primordial dust closer to the Sun. The general mission concept, called TPFY, would be able to take family portraits of planetary systems around the nearest 1,000 stars, where each planet would appear as a single pixel in the TPFY's detectors, rather than providing blue marble images of alien Earths. One could identify whether a world has oceans, rocky terrain, or thick gas envelopes by measuring the pixel's color. The detection of atmospheric carbon dioxide, water vapor, and the potential biosignatures of oxygen and methane would be possible if its light were broken into a spectrum. The bulk geography of the planet, including the locations of its ice caps, oceans, continents, and seasons, could be discovered by monitoring the pixel's brightness variations over months and years. Future larger interferometric arrays that employ formation flying and laser communication to reach baselines of several thousand kilometers will be made possible if the Roadmap interferometric mission is successful. These missions could replicate the Apollo Blue Marble and build habitable worlds around other stars. To make room for TPFI, a precursor mission called the Space Interferometry Mission, SIM, would launch. To find the astrometric wobbles of any companion Earth mass planets in their habitable zones, the original plan for SIM called for stringing 7 tiny mirrors across a large boom to search over 100 nearby stars, providing an interferometric baseline of up to 10 meters. Because of Goldin's passion and the Clinton administration's unspoken support, NASA quickly approved SIM and formed working groups to complete TPFI plans. Both projects eventually encountered significant problems. SIM achieved or surpassed important developmental milestones with a strong initial funding surge. However, by the mid-2000s, the project's funding had dropped to a dribble due to the Bush administration's new Constellation program and the skyrocketing costs of JWST. Most astronomers were unconcerned about SIM's hyperspecialization because it seemed to have little use for the general public. Many planet hunters hoped to get around SIM's hyperspecialization to create a more powerful TPF because they felt it was unnecessary. 2010. SIM quietly ceased operations after spending over $500 million, discarding or reusing all of its flight hardware. Another issue with TPFI was that its working groups discovered that the initial estimates for the mission's cost and launch date were overly optimistic as they examined the associated technical challenges in greater detail. This occurred due to the mission's frequent downgrades and launch delays, which increased needless costs. It would be expensive and challenging to cryogenically cool each mirror. The entire assembly would vibrate if reaction wheels were needed to turn and aim the mirrors on their long boom, which could compromise observations. By removing the long boom and substituting a free-flying array of multiple mirrors to gather light and channel it into a central beam. Combining Hubble, Darwin, and related theories would eliminate vibrations. Several new designs were introduced by the European Space Agency's TPFI project, Darwin, which called for 5 or 6 cryo-cooled spacecraft to fly in formation in deep space with centimeter-level precision. This would significantly increase the mission's complexity and the propellant needed. TPFY's original cost estimates of $1.5 billion would, at the very least, skyrocket due to the uncontrollably high-cost growth of the intricate, cryogenic JWST, making it even more prohibitively expensive than its predecessor. By 2001, JPL had rescheduled the launch date of TPFY to no earlier than 2014, and mission planners were looking for less expensive alternatives, especially a single non-cryogenic telescope. The conventional wisdom was that the light required for interferometry was too great for a single filled aperture telescope to image the slick, wave-like behavior of Earth-like exoplanets. The light must be carefully controlled, and the star's intense glare must be eliminated to record the 10 billion photons that an alien Earth would emit at optical wavelengths. Starlight flows in liquescent wavelets when it hits a single mirror, pooling and puddling in frozen ripples and coruscating speckles around even the smallest surface floors. Light from a distant star resembling a point would still scatter off the edges of an ideal circular mirror, creating a central bright disk encircled by concentric rings. This would even happen with a mathematically perfect mirror, only seen in late-night fantasies and computer simulations. Numerous disks, rings, ripples, and speckles tended to appear in a star's image, exactly where one would anticipate finding any potentially habitable planets. They would be 8 orders of magnitude more colorful than the faint light of any nearby small rocky worlds. But planetary detections would be unlikely, if not impossible, as each asteroid would normally only be 1/100th as bright as a target star. No modern optics textbook offered this scientific consensus at the start of the 21st century, and it was completely incorrect. A coronagraph device that could theoretically blot out a star's diffraction, disks, and rings was necessary for a single telescope TPF solution. A coronagraph is any occulting object positioned in front of a telescope's mirror to block out unwanted light from a target star. It was created in 1930 by the French astronomer Bernard Liot to allow observers to see the Sun's hot, nebulous corona. To see a coronagraph in action, make your own. Using the same idea, place your right thumb over the Sun's disk in the sky to protect your eyes from most of its glare. You may notice that a small amount of sunlight still diffuses around the edge of your thumb, even if the sun is completely blocked. You can minimize extra glare and add another barrier that keeps the sun out of your vision by positioning your left thumb just behind your right. Similarly, Liot created a series of pupil lenses, partially transparent masks, and disc-shaped opaque stops for his coronagraphs, which gradually eliminated the remaining light that had been dispersed off the edges of the original occulter. The Sun's corona, which is 1,000,000 times fainter than the Sun itself, could be imaged by Liot's apparatus. However, their apparatus fails to achieve the 10 billion to 1 starlight suppression needed to image an exo-Earth in space because it leaks far too much stray light into a telescope's visible optics. Given the growing complexity of TPFI, astronomers Wesley Traub and Mark Kuchner of the Harvard-Smithsonian proposed a new class of coronagraphs in 2001. More specifically, these coronagraphs used interferometric principles to suppress starlight. Researchers discovered that they could increase the amount of starlight blocked and redirect the remaining starlight to a thin region on the edge, away from the dark shadow in the center of the coronagraph, by carefully altering the shape of the stop and adding interferometric nulling patterns of spirals or bars to a coronographic mask. 99.9999% of a star's light was blocked by this. A star's light would be blocked, cancelled out, and then carried away to the detector's edge, while the faint glow of a nearby planet would flow through without any issues, creating an image inside the shadow. The plan worked nearly perfectly in closely monitored lab tests. While the coronagraphs of Traub and Kuchner were easy to make, each mask usually performed well for a small range of light wavelengths, rather than the entire spectrum of a star. Another astronomer, David Spergel of Princeton University, independently developed a different configuration of shaped coronographic masks and students that achieved extreme starlight suppression after Traub and Kuchner developed their coronagraphs. After taking notice, JPL and NASA began supporting the development of a coronographic TPF, called TPF-C, a planet-finding telescope that uses optical light rather than infrared. The original idea for TPF-C, which emerged quickly, called for using a large 8-meter monolithic mirror to suppress starlight by connecting to one or more specialized coronagraphs inside the telescope. The segmented foldable mirrors, such as those used by JWST, created too many wavefront aberrations to be compatible with the ultra-sensitive coronagraphs, and the monolithic primary mirror would be oval, rather than circular, to fit into a rocket fairing. More coronagraph designs appeared after the discoveries of Traub, Kuchner, and Spergel. Starlight can be suppressed in countless ways, such as by phasing it out and scattering it with masks and lenses. twisting it with networks of spiraling vortices, or weakening it with labyrinths of grooves. A small amount of undesired light did, however, make it through. Perfectly symmetrical wavefronts of light had to be piped to and through the coronagraphs to reinforce the null order. The amount of photon scattering into other telescope regions is called the order of the null for each design. Since a collimated beam of starlight would almost imperceptibly walk across new paths, veering over different patterns of flaws in the mirrors, even the smallest percentage of pointing error in the telescope's guidance would weaken the null order. It would be necessary for TPFC to point with more accuracy than 5 times that of the Hubble. On the reflective surfaces of the telescope, any surface deviation smaller than the diameter of a single silicon atom would result in less than perfect wavefronts, weakening the null order. The mirrors on TPFC would need to be about 100 times smoother than those on Hubble. Even though producing and maintaining such precise points and figures would require major and expensive improvements in active optics, vibrational control, and mirror manufacturing, those tasks still appeared to be less expensive than any possible TPFY mission. NASA and JPL chose TPFC because of its probably lower costs, even though it may be able to search fewer stars for potentially habitable worlds and has a lower sensitivity and capability than TPFI. Year after year, TPFC's performance improved, while TPFY's declined. Seeing the shift, JPL hired Traub, 2005, as chief scientist for NASA's exoplanet science programs, and as a project scientist for TPFC. He would oversee a staff of about 50 employees who would invest $50 million annually in whatever it took to get TPF operational on schedule. If he took the job, he would have to leave Massachusetts and move across the nation. He was getting close to 70 and knew that leaving would also mean breaking off long-standing friendships. Traub, however, decided to accept JPL's offer right away. In 10 years, if all went as planned, he would be in charge of TPF's team as they conducted observations and sifted through the collected light from other far-off, habitable worlds, making the new opportunity worthwhile. Traub may be one of the lucky few to discover life beyond Earth and the entire solar system, out of all the people who have ever lived, past, present, and future. He could be a major contributor to the biggest discovery in human history since the discovery of fire. Soon after, Traub relocated to sunny Pasadena and rented a small apartment. Spergel's work, that of his Princeton colleague Jeremy Kasdin, and Webster Cash of the University of Colorado, were the main influences on developing a third technique for blocking starlight as the trajectories of TPFC and TPFI diverged. The high tolerances needed for TPFC's mirrors worried all 3 researchers. It would operate as a free-flying, autonomous spacecraft outside the telescope, keeping any stray starlight from entering the optical train. Instead, they suggested erecting a coronagraph outside the telescope to let in all that corrosive, tainted starlight. They dubbed the free-flying coronagraph a star shade. Their performance simulations showed that the best shape for absorbing and blocking out starlight would be a multi-petaled sunflower. A star shade would cast a deep shadow onto any telescope, enabling more broadband spectroscopy to expand the search for biosignatures, in contrast to TPFY or TPFC's starlight suppression techniques, which only worked in a few wavelengths and required reams of specially made kit. The telescope, for a star shade, could be any space observatory with a large enough general-purpose mirror, like NASA's proposed JWST. It wouldn't need cryogenic cooling like TPFI or ultra-smooth monolithic mirrors like TPFC. However, constructing and running a star shade would be difficult if many of the TPFC telescope's extreme tolerances were transferred to another spacecraft. Most designs called for a star shade with a 50 to 100 diameter, a gossamer thin and razor-sharp edge, and a coating of dark, anti-reflective materials, floating between 50,000 and 150,000 kilometers in front of a space telescope. It would take extraordinary orbital control to align the shadow of a star shade with a telescope, since the Earth and the Moon are typically 380,000 kilometers apart. To maintain its massive shape to sub-millimeter accuracy and autonomously unfold in space, the star shade must use tiny high-impulse thrusters to stay on or slew between targets. Unlike an agile TPFC that could do so in seconds or minutes, a star shade would require days or weeks to switch targets. Compared to TPFC, a star shade would examine fewer stars, but it might be less costly overall. The starshade concept was eventually dubbed TPFO. The letter O stands for Occulta by NASA's mission planners, but they put it on hold for years because it was considered so late and seriously. TPF comes in 3 varieties: I, C, and O. After almost 10 years of intensive research, NASA, JPL, and other relevant organizations identified 3 general technologies that could each produce images of habitable planets around other stars. Their political taskmasters did not give them the money or power to choose an architecture and move forward. To everyone's delight, the mandate was announced in a statement hidden in the supporting materials for President George W. Bush's 2004 vision for NASA, the vision that established the Constellation program to return humans to the Moon and Mars. Traub reflected fondly on the main topic of our discussion, which was that the summer of 2012 had faded into the distance long after TPF had made its initial promise. Tall and reserved, Traub has soft blue eyes. JPL. Traub found a stoic acceptance that it would be difficult to mobilize enough community support to fly even 1 TPF mission shortly, let alone 2. He continued, "There was a feeling that, well, we definitely weren't going to be able to undertake 2 missions simultaneously, and it wouldn't be happening as quickly as this letter claimed. But that was fine. We would put a lot of effort into writing the reports on science definitions, refining the technology studies, and making an impression on everyone. We might go on for a couple more years, but that would be it. I hate to tell you that science isn't everything. In actuality, people frequently think about it last. People support what directly benefits them, rather than what they believe is best for science. Today, full employment for astronomers is the aim of the astronomy community. The broader US astronomical community's outspoken support for the project declined as it became apparent that constructing both TPFs would likely cost billions of dollars. The decision became evident as NASA struggled to balance the conflicting needs of astronomers with the financial burden of its human spaceflight initiatives. Astronomers. It diverted about $3 billion from its science budget in February 2006 to fund Bush's Constellation program and a few space shuttle missions. Lofty ideas were left in tight funding limbo when the agency effectively shelved the hurried push for life-finding space telescopes and relegated it to one of its many unfinished technology development projects. NASA appeared destined to postpone any planet imaging telescope deserving of TPF until at least the mid-2030s, unless funding and policy changed dramatically. Meanwhile, we would keep finding more worlds that might resemble Earth. Traub told me that maintaining a positive outlook had become part of his job description when I asked him about TPF's prospects in his lifetime. From a professional standpoint, I can't give up, because doing otherwise would be incredibly disheartening, he said, disclosing that the project he had moved to JPL for had failed less than a year after he joined. But once you begin constructing a cathedral, you don't have to finish it before you pass away. They usually take a few hundred years to finish. But here, we're not constructing cathedrals from the Middle Ages. This is an easier task, in my opinion, and I'm sure that we would have been operating these telescopes by the deadline if everything had gone according to the 2004 letters plan and we had obtained the required funds. TPF-I might be at the end of the decade, and TPF-C would be getting close to launch. Since 2004, I have not discovered anything essentially new that would alter that opinion. None of this is straightforward from a technical standpoint. This task is more difficult than anything I've ever done, as everyone involved would agree. But now we have 6 ways to find exoplanets that might be habitable based on their light. In the lab, we have shown them. Instead of creating new things, we need time to fix the engineering. All you have to do is construct a big mirror with a small piece of glass in the center. Place it inside a massive rocket and add some deformable mirrors to the rear. According to Traub, who shook his head, there are no financial incentives for anyone in the private sector to invest in a project of this size. I proposed that if it were that easy, there might be alternatives to NASA. Instead of government support, private funding might be the solution. The government acts this way because those with extra cash find it nearly impossible to invest in a long-term project like this. The decision to send men to the moon was made by President Kennedy, not NASA. While lawmakers and the administration decide what NASA should do, a member of Congress or the president will feel strongly about this and realize that the first discovery of extrasolar life is a once-in-a-lifetime event. Did we make mistakes, fail, and give up? Our political leadership only needs to recognize this is a significant issue for NASA and our country. If we are given the all clear, I can assure you that we know exactly how to proceed. Here are my thoughts on the matter. In late May 2011, Traub and I had a brief meeting on the glass-covered top floor of the famous Media Lab at the Massachusetts Institute of Technology in Cambridge. The conference, The Next 40 Years of Exoplanets, was organized by MIT planetary scientist and astrophysicist Sara Seager to reflect on the field's turbulent recent past and possible future redemptions, which could take place within TPF or in other unthinkable ways. Seager requested that Traub address the Kepler findings and defend JPL's contribution to the growth and decline of TPF. She had also invited several other prominent people. Matt Mountain had come to argue for a poor man's TPFO, describing how a starshade could provide spectra of any minor rocky worlds surrounding a few nearby stars, using less than 1/10 of JWST's observing time. Even though NASA is reluctant to spend more than it needs to launch its developing space science fleet, he calculated that a JWST starshade would cost about $700 million. According to John Grunsfeld's appearance, who appeared to be getting ready to return to NASA, American astronauts were ready to take on difficult tasks, like setting up and maintaining planet-finding telescopes in far-off deep space. Any species that only exists on one planet will eventually go extinct, his inner Tsiolkovsky told him. The conference was perfectly sparked by Seager. Additionally, he predicted that a NASA space telescope would conclusively confirm the existence of the first habitable exoplanet on the Moon on July 21, 2025, the 56th anniversary of the first human landing on the Moon. On the eve of her 40th birthday, she was still comparatively young, with the energy and endurance to continue leading the field of exoplanet research for the next 4 decades. Despite her youth, she was already one of the field's most respected and successful professionals. She started a career in astrophysics to gain more knowledge about cosmology and the early stages of the universe's formation. she instantly veered off course when the exoplanet boom started. Seeger conducted the first comprehensive theoretical modeling of the composition and evolution of hot Jupiter atmospheres in the mid-1990s, while he was a graduate student working for Harvard astronomer Dmitry Sasolov. Some astronomers at the time thought Seeger and Sasolov's work was dangerously naive, and many still thought that hot Jupiters were the result of stellar variability and wishful thinking. However, the astronomy community finally recognized the existence of hot Jupiter in 1999, after Seeger earned her PhD from Harvard, and her models became the standard for observational research. Seeger responded by leaping forward once more and explaining that it was possible to investigate the atmosphere of a hot Jupiter, transiting without constructing a structure similar to a TPF. In her proposal, co-authored with Sasolov, Seeger pointed out that astronomers could use the existing ground space-based telescopes to detect the spectroscopic information that would be blasted toward Earth by starlight blasting through the planet's upper atmosphere. She advised searching for it because she thought sodium should have a distinct spectroscopic signature in optical wavelengths. At that time, scientists had not found any transiting planets. A few years later, a team tested Seeger's theory using the Hubble Space Telescope to observe a recently discovered transiting hot Jupiter. The sodium spectral lines, the first indication of an exoplanet's atmosphere, were discovered as expected. As time passed, Seeger's attention turned to the hunt for extraplanetary life, where she made significant advances in characterizing potentially habitable world environments. Throughout her life, she'd stated that she would like to pilot any upcoming TPF flight. Seeger, who organized the Future Focus conference, videotaped every activity and posted it online. She made a strong, thin impression when she opened her remarks to the scientists, engineers, and journalists seated there. Her somber face was framed by her knee-high boots and shoulder-length dark hair, which matched her blazer and funereal black A-line dress. She encircled her neck with a blood-red scarf. Although she spoke with the same steely, sharp intensity as usual, which some of her co-workers found unsettling, this was not a sign of a lack of empathy or social disengagement. Through her algorithmic communication style, sudden declarations of sincerity and calculated charm, Seeger showed how her mind was always overclocked, processing information more quickly and intensely than most of her fellow humans could have ever guessed. While speaking, Seeger glanced around the auditorium at the assembled audience, but frequently, when making her most compelling arguments, she stopped to look straight into the camera, speaking to an anonymous group of future generations. I called the conference to plan how to continue the wave of discovery in the field, despite the apparent decline in the exoplanet boom and the budget crisis facing the US government, she said. Most of us who work on exoplanets believe that when people look back on our generation, hundreds or thousands of years from now, they will remember us as the first to discover Earth-like worlds. I don't mean Earth-size or Earth mass. She said she no longer thought those findings were inevitable as she approached her 40th birthday halfway through her life. To make an impact, I brought you all together to record this. We will be remembered as the ones who initiated the future of other Earth-like worlds, not as individuals, but as a group. That is the reason we are here. Even though everyone agreed that finding potentially habitable and possibly living planets around nearby stars was essential to the field's sustainability, there were sharp differences in opinion about how this search should proceed. It would not be straightforward to forge a common course for the ensuing years. A longtime friend of Seeger's and current Harvard professor interested in planet hunting, David Charbonneau, stood up from the audience to argue against pursuing a mission similar to TPF. Charbonneau was in charge of the group that used Seeger's method to find the first exoplanet atmosphere. The phrase, "bigger than Traes 4, emblazoned on his bright yellow t-shirt, referred to a transiting planet he had helped discover in 2007, which was so light and fluffy that it could float on water like a piece of balsa wood. One of Charbonneau's specialties was oddball transiting worlds. He gained notoriety in 2000 after discovering the first one, a hot Jupiter, circling the Sun-like star HD 2009-458. He had devoted much of his time since 2009 to the Earth Project, pronounced MIRTH, a ground-based array of tiny 0.4-meter telescopes that looked for transiting super-Earths, or M-dwarfs, around nearby red dwarf stars. Given the comparatively large size of the super-Earths together, the smaller size of an M-dwarf around our Sun, and their comparison to our own planet, the super-Earth M-dwarf pairing was the easiest to observe, and likely the least expensive to describe among all potentially habitable planetary systems. Charbonneau stated that, without the need to construct a multi-billion-dollar TPF, transiting super-Earths would be ideal targets for transmission spectroscopy, as initially proposed by Seeger and others. The thick atmospheres of these enormous worlds are likely extraterrestrial, and their more powerful gravitational fields compress their landscapes. Empirical evidence did not support debates about whether or not super-Earths could have plate tectonics to stabilize their climate, similar to our smaller planet. M-dwarf super-Earths would have to be dangerously close to their small, dim stars to have liquid water on their surfaces. This would be necessary because the tidal forces created by the nearby star would deplete the energy from the planet's rotations, causing many of them to lock one face toward their stars, just like the Moon does, to Earth. On such worlds, a thin ribbon of perpetual middling twilight would separate the two hemispheres, one covered in unending night and the other permanently scorched by ionizing radiation from stellar flares. The atmosphere of a tidally locked planet may completely freeze into the night sky, or if it continues, it may generate constant gale-force winds between the different hot and cold hemispheres, depending on its composition. No M-dwarf super-Earth appeared likely to ever be at the top of a list of exoplanetary real estate that resembled Earth if they were even habitable. Charbonneau did not place much importance on the fact that transit studies could only uncover a vanishing fraction of the local population of exoplanets, nor on the environmental disadvantages and uncertainties involved. Finding and studying transiting M-dwarf super-Earths quickly and affordably without waiting a generation or more was crucial. His argument summed up a growing view in the exoplanet community that it was practically impossible to directly image Earth-sized planets in the habitable zones of Sun-like stars because it was so difficult. In place of TPF, several smaller, less ambitious and less capable ground space-based mission proposals have emerged to support the astronomers during their challenging budgetary times. The Kepler mission, known for its focus on searching for transits around nearby stars, inspired most of these proposals. 2 years later, NASA would set aside $200 million to launch TESS, the transiting exoplanet, one of those low-key proposals, in 2017. Examine the satellite. TESS would replace NASA's Kepler mission, which would search the entire sky for transiting planets orbiting stars within a few hundred light-years of Earth. Charbonneau sharpened his presentation by pointing out that there were almost 250 M-dwarf stars within 30 light-years of our solar system, compared to just 20 Sun-like stars. According to Charbonneau, who extrapolated from Kepler results that indicated a large number of close-in, low-mass planets were harbored by smaller, more excellent stars, we are guaranteed that there are potentially habitable bodies at the right place around those M stars to transit as viewed from Earth within a maximum of 20 light-years of the Sun. In addition to the lack of funding, he believed pushing for TPF was a mistake because it's foolish to devote 20 years of your life to something with too narrow a vision, given the rate of discovery. Younger astronomers, according to Charbonneau, would not and should not be willing to make such a long investment in uncertain returns. Missions like TPF and AT-LAST would remain doomed to wither and die on the vine for decades to come, and knowledge of any true Earth analogues would remain elusively out of reach. It was unavoidable. Following a brief pause, American planet hunter Jeff Marcy strode forward to subtly criticize Charbonneau's rejection of large, difficult space telescopes, implying that it was misguided and ineffective. Unusually, he stared at the floor as he restlessly shifted his weight from foot to foot and started his remarks with his hands stuffed deep in his pockets. He claimed to be thrilled by Kepler's performance, but also incensed at the lack of advancement over the previous 10 years and the lowered expectations for the upcoming one. He claimed that Kepler's findings made the case for a TPF extraordinarily compelling because they pointed to numerous non-transiting, potentially habitable worlds that would otherwise be difficult to closely examine orbiting nearby stars. He took his anger out on NASA and the vassal-like space science community, accusing them of serious leadership failures. Somehow, NASA blinked, despite TPF being the only plausible future for astrophysics, promising high resolutions only achievable through unfilled apertures. In his picture, the exoplanet researchers were split into opposing, clashing fronts that cancelled each other in pulses of self-annihilative incoherence, as if the agency and JPL were interferometers. This profoundly impacted the foreseeable future of the field, relegating the collective dream of a TPF to the murky realms of space astronomy. He recalled being a member of the first TPF science definition team in 1999 and said, "This is the history as I know it painfully well." The administrator at NASA headquarters scolded us with a shaking finger in 2000, telling us we needed to construct TPF-I and enroll in astrobiology and molecular biology courses. In 2002, NASA recommended building a coronagraph instead of an interferometer, citing insufficient funds for both. Then, astonishingly, NASA headquarters declared in 2004 that we ought to construct both. An interferometer is in the infrared, and a coronagraph is in the optical. He shook his head angrily. I couldn't understand how the money suddenly appeared to fund both TPFs. These two designs, the coronagraph and the interferometer, were at odds for many years. Those were a difficult few years, in my opinion. Then, the occulter appeared and started to shadow the entire field. The audience erupted in laughter, not so much because of the direct joke, but to ease the tension that followed the disclosure of so many upsetting facts. Marcy ended his presentation by stating that the TPF's failure had seriously damaged his confidence in NASA, leading him to wonder if the agency should not completely outsource some of its excessive portfolios to the more flexible private sector. In addition to TPF, he had one other significant and meritorious objective for the agency over the ensuing 50 years, which he communicated to President Obama in a direct Tsiolkovskian appeal. "Get up and make the following announcement," Marcy begged, adding, "Send a probe to Alpha Centauri, the triple star system, before the end of this century, and return images of its planets, comets, and asteroids as soon as possible, even if it takes a few hundred or 1,000 years to get there. It would be a fantastic mission to visit Centauri Alpha." The involvement of Congress, every aspect of our society, and K-12 students would be significant. If we're lucky, this could revitalize NASA. Any such mission should be worldwide, encompassing those in China, India, Japan, and Europe. An expedition to Alpha Centauri would further science and give the world diplomatic coherence. A few audience members laughed again, albeit with a bitter cynicism. The country was deeply indebted and divided politically and financially. The notion that any American politician, let alone the president, would choose to use even a small sum of political capital to try to reach the stars, in the face of such formidable challenges, was evocative of the same idealistic thinking that had made the TPF project disaster years prior. Seeger was back in front of the crowd a short while later. Due to the controversy surrounding Charbonneau and Marcy's remarks, she largely scrapped her planned speech. Seeger reiterated, "We want to go out and map the nearest stars, establishing a consensus everyone could support. When people embark on their interstellar journey thousands of years from now, they will remember us as the ones who found planets like Earth around the closest stars." I want to say that I love NASA because it has been helpful and has had a big impact on my career. However, I also don't think NASA can finish the terrestrial planet finder within the next 40 years. I now realize I am one of the most ardent supporters of any mission involving a terrestrial planet, as everyone in this room knows. That's what I want to achieve. I hope to have a TPF in my lifetime, but I haven't really worried about it yet. Her eyes and voice briefly conveyed a sudden tinge of sadness. As a tenured professor at MIT, Seeger stated that she had a tremendous deal of security, which allowed her to pursue high-risk, high-reward research almost as a duty. Losing faith in NASA's ability to reach TPF in her lifetime had forced her to. Consider new advancements and different approaches. The recent rise of a new generation of commercial spaceflight providers, including a few high-tech startups building spaceports and rockets to finally escape the crippling paradigm of high launch costs, was especially encouraging. Multi-millionaire CEOs who had made fortunes with companies such as PayPal, Amazon, and Intel led SpaceX, Blue Origin, and Xcore. Seeger thought the new companies could finally provide the profitable, sustainable human expansion into space that NASA had not been able to. They might be a powerful tool for accomplishing an elusive objective, initiating the next wave of synergies astronomers needed to lower costs and speed up the launches of TPF-style space telescopes by bringing the light of other living worlds into the lives and careers of everyone gathered in the room. She had called a gathering of her friends and colleagues to talk about the field's future and bid it farewell for the time being. She would continue her exoplanet research, but a fresh, all-encompassing emphasis on fostering the growth of a self-sustaining commercial spaceflight sector would challenge it. As a result of the unexpected announcement, the crowd started to whisper. With unwavering resolve, Seeger clarified, "That's what I'm going to be doing now. Most of you haven't seen me at meetings recently, and you won't see me very often in the future due to my investment in this project. If you see me working on Mars and asteroids, you'll understand that I'm not particularly interested in those projects." She provided launch cost estimates, stating that a ride on a more basic Russian Soyuz rocket only cost $10 million, whereas it had cost roughly $100 million to reach orbit on one of NASA's space shuttles. "I'm interested in helping the commercial spaceflight world in any way I can," she expressed. "Commercial providers might be able to cut launch expenses by a further order of magnitude. We cannot complete terrestrial planet finder at $10 billion, so we must ensure their success. If we assist them in overcoming this obstacle, they will succeed." After Seeger's presentation, the audience filed out of the auditorium and into the hallway, huddled in loose pockets of coffee-fueled conversation. I overheard a biologist explain to an astrophysicist that the 1990s race to sequence the human genome was comparable to the hunt for a space telescope that could detect life. The biochemist said, "Many groups had the technology, just trashing each other. The government, academic institutions, and pharmaceutical companies then attempted to arrange it in a way that best served their objectives. Competition from both the state and private sectors motivated everyone to achieve the goal. It would be beneficial if you could figure out how to convince China to find the first habitable planets and give them all Chinese names." A scientist was told by the coffee and tea tables that all he needed to send a robotic probe to Alpha Centauri at 10% of the speed of light was a nuclear reactor from a Virginia-class submarine coupled to a high-impulse electric propulsion system. With the technology of today, we could succeed. The engineer let out a cry. We would probably still be present to witness the returned pictures. The scientist's only response was a polite nod, implying that the engineer had forgotten some crucial information in his calculations. That evening, when the conference was officially over, some attendees relocated from the media lab to Seeger's office on the 17th floor of MIT's Building 54, the Green Building, Cambridge's tallest skyscraper. At Seeger's invitation, some of us climbed to the rooftop, which was decked out with antennae and white radar domes, to gaze down at the sailboats cruising the calm waters of the Charles and the glittering lights of Boston's skyline. River. While admiring the view, Mountain, Seeger, and Grunsfeld whispered. Trauben sat quietly for a while, watching the sunset. After climbing beneath the massive radar dome to snap a few pictures, Marcy descended. When pressed, he would return to talking about NASA's situation, but he mostly engaged in small talk. He later told me that NASA was having a lot of problems. Despite its resources and experience, it cannot surpass the private sector. It is unable to overcome its own bureaucracy. How did NASA manage to overlook TPF? While it's possible that NASA is not at fault, I prefer not to assign blame. Perhaps we encounter challenges when we strive to organize ourselves to achieve great things. Rome falls apart. Humans are not perfect. We make genuinely terrible mistakes. He held up an empty hand containing a single grain of rice, with his thumb and forefinger angled like chopsticks, and said, "Apparently, this is our nature. This is the extent of our superiority over ants. That's my perspective. We operate similarly to a colony of bees. It's organic. However, there's also a condition known as colony collapse disorder." A drift of people surrounded Seeger, the queen bee of this temporary hive, as the conversations continued inside the Green Building. Standing at its edges, I heard her muse about interstellar travel again. She remarked, "I don't know if we'll ever leave the solar system. All I know is that having the option would be nice, into the desert areas. Our sun is the source of an expanding shell of light that envelops our solar system. The Milky Way's spiraling galactic plane contains thick lanes of gas and dust that extinguish some light, causing the shell's midsection to taper like an hourglass, rather than being perfectly spherical. The sun's photonic shell ripples outward in twin lobes, constantly expanding at the speed of light above and below the galactic plane, which is comparatively clear of obstructing debris. Even though the boundaries of the shell sweep 300,000 kilometers farther away from us every second, their expansion through the vast intergalactic voids is so glacial that we can estimate their position at 4.6 billion light-years away. The initial burst of photons from the thermonuclear ignition signaled the birth of our star and formed the edges of the shell. Planetary reflections, refractions, and starlight occultations record every moment of our solar system's history as it unfolds. When our sun, which has long since swelled into a pulsating red giant, finally burns through its remaining stores of hydrogen and helium, this photonic broadcast will likely end. It will leave behind a stellar remnant, a white-hot carbon and oxygen ash ember, scorched planets, and an evanescent ionized gas nebula. The remnant's dim light will eventually turn black as it cools over the ages, cutting off the solar transmission as surely as scissors cutting a thread. Only the light of the past will remain to reverberate for all eternity. We observe it from a dwarf galaxy within the large Magellanic Cloud, and the Milky Way's echoes of primordial and Precambrian time, the formation of planets, the emergence of life on Earth, the oxygenation of our planet's atmosphere, and the invasion of the land, were born on photons and long since left the Milky Way to wash over the nearby galaxies, galactic clusters, and superclusters. An observer would see the Earth of 2.5 million years ago, when the ancestors of modern humans were perfecting the production of primitive stone tools in sub-Saharan Africa, somewhere among the trillion stars of Andromeda, our nearest neighboring spiral. The glacial advance of 160,000 BC would trap our world, swooping close to the Milky Way, with our ancestors poised to flee Africa as the ice sheets receded. The echoes are closer to home in our own galaxy. The Earth appears as it was during the emergence of agriculture and the Bronze Age civilizations of Mesopotamia, Egypt, and the Indus Valley, amidst the open clusters and blue hypergiant stars of the Carina Nebula, located between 6,500 and 10,000 light-years away. Light from the Earth of Thales, Democritus, and other ancient Greeks now sweeps the glistening molecular clouds and blazing newborn stars of the Christmas tree cluster, just over 2,500 light-years away. The Earth has recently initiated radio transmission and perfected its internal combustion engine in the skies of the giant planets orbiting the Sun-like star HR 8799. The news of the 1969 Apollo 11 lunar landing has just reached the aging yellow suns of Capella, while the first television broadcasts from the 1930s are now rolling over the ice-blue stars of Regulus. We cannot determine whether this has truly found an audience. The Earth-based live broadcast may be the only one in the universe. The beginnings and development of our solar system would paint a spooky picture if seen from the vicinity of the nearest stars and condensed into a brief time-lapse film. A massive black cloud of molecular hydrogen gives rise to a star, followed by spinning planets. Under their whirls and bands of swirling gas, the outer giant planets remain relatively inert and peaceful for billions of years after settling into their orbits. After the magma oceans cool and crust over, even less occurs on the innermost part of Mercury. The other three inner worlds are a blue-green gem of land, sea, and clouds. But Mars withers and freezes, and Venus quickly bakes under a pall of steam. For most of the film, Earth, the system's most peculiarly fluctuating world, is a kaleidoscope of roving continents, throbbing glaciers, erupting mountains, rushing tides, and swarming greenery. In the final second, before the time-lapse catches up to the present, we add electric lattices of nocturnal lights and glittering halos of artificial satellites to the Earth. The altered planet ejects a few metallic flecks, resembling spores throughout the system. Before they launch at solar escape speeds to unidentified locations in the galaxy and beyond, 5 approach Jupiter. All of humanity's early interstellar probes were launched by NASA. Pioneers 10 and 11, Voyagers 1 and 2, and the New Horizons spacecraft headed for Pluto. At a distance of more than 6 billion kilometers, high above the solar system and outside Pluto's orbit, the fastest and furthest of those probes, Voyager 1, turned its cameras back toward Earth for the final time on February 14, 1990. The system's ecliptic plane. At the request of Carl Sagan and other Voyager mission staff, the spacecraft was designed to reproduce the iconic Apollo blue marble image from 100,000 times farther away. From that distance, the Earth was almost completely hidden by the Sun's diffractive radiance. But a closer look at the transmitted image from Voyager 1 showed that our planet was only a single azure point of light that made up less than 1 pixel. Sagan used the phrase pale blue dot to describe the image of Earth and used it as the title of one of his numerous best-selling books. He had reached the highest level of space science practice and popularization in the decades following the Green Bank meeting, producing the immensely popular television miniseries Cosmos and conducting important research on planetary atmospheres. Sagan assembled a long-playing phonograph record with Frank Drake and other partners, which the Voyagers sent to the stars. Each spacecraft fastened a copy of the copper, aluminum, and gold record to its side. The record arrived complete with a stylus, a magnetic cartridge, and pictogram instructions, ready for playback. In the void of interstellar space, each record ought to endure for countless ages, surpassing both the Earth and the Sun. Our first contact with another planet is unlikely, but a highly advanced civilization, traveling between the stars, will likely recover the records if we do. The conceitedly utopian Voyager records, which did not mention entropic human failings such as crime, war, famine, disease, and death, contained greetings in 54 languages, 118 happy photographs of life on Earth, and recorded messages from President Jimmy Carter and UN diplomats. Each would share the sounds of wind and rain, heartbeats and laughter, kisses and rocket launches, whale songs and electroencephalograms, music by Stravinsky and Mozart, Bach and Beethoven, Javanese gamelans, Peruvian panpipes, and Chuck Berry's version of Johnny B. He would play good on his electric guitar, each a golden memory of creatures, long since transcended into an unknowable future, form or fallen from their primordial defects, each a whisper from the dead Earth. To many earthbound and humbled souls living in a universe growing more remote and cold by the year, Voyager's vision of the far-off Earth and its messages to the stars became beacons of hope, tenacity, and wisdom. Pure and noble manifestations of the better angels of our nature. Writing about the pale blue dot, Sagan poetically referred to it as a mote of dust suspended in a sunbeam, calling it the aggregate of our joy and suffering. There is no indication that assistance will arrive from somewhere to save us from ourselves in our obscurity, in all this vastness. At the moment, the Earth is the only planet known to support life. We make our stand on Earth, and there is no other place where our species could migrate, at least not anytime soon. Sagan interpreted the image as representing the cosmic folly of human divisions and geopolitical conflicts. Everyone you love, know, and have ever heard of, every human being who ever was, lived out their lives. The pale blue dot, he reasoned, was a rough representation of Earth as viewed from a starship landing after a long interstellar journey, and while he may have thought about it, he did not mention that it replicated the appearance of our planet through a first-generation TPF-style space telescope. Earlier in the same essay, Sagan addressed the difficulties of finding any viable future planetary home for humanity, writing that we would know from experience that our home planet's pale blue came from its life-giving seas of water and clouds of water vapor. A more detailed analysis would be required. On December 8, 1990, Sagan coordinated a series of Earth observations with the Galileo spacecraft, passing our planet on a roundabout journey to Jupiter. That inspection came 10 months after Voyager 1's historic image. From the depths of space, and using only first principles, Sagan and the Galileo team successfully verified Earth's habitability and then identified its biosphere and technology by analyzing it as though it were a recently discovered alien world. They verified the composition of light in the planet's polar caps, seas, and clouds by measuring its temperature in infrared light. They discovered evidence of life in the oxygen-rich, methane-tinged atmosphere, which was far from thermodynamic equilibrium, and in the continents covered in vegetation, which reflected the spectral sign of light-absorbing chlorophyll from photosynthesis out into space. The planet's surface sent strong pulses of narrow-band modulated radio waves that suggested a technologically advanced civilization. The general consensus was undeniable. Life existed on a large portion of the planet, and someone or something there had the intelligence to establish a worldwide communication system. When Sagan and his group later aimed Galileo's instruments at the moon, they were unsurprised to discover that it was a barren, lifeless rock, in contrast to our planet. Despite their apparent pettiness and banality, Sagan's Galileo observations were a powerful control experiment and a standard of proof that could be applied to any planet, whether studied by a close-flying probe or by light collected by telescopes across interstellar distances. When looking at the scope of his later work, it is difficult to avoid the conclusion that Sagan was systematically preparing for any observational studies of potentially habitable exoplanets that might take place during his lifetime. We'll never be certain. After a 2-year battle with bone marrow disease, he passed away in December 1996 at the age of 62, just months after NASA Administrator Dan Goldin had announced plans to build TPF. Sagan was still as nimble-minded and sharp as he had been throughout all the previous decades of his scientific career. Had Goldin's original predictions for TPF's 2006 launch come true, Sagan would have been 72 years old when the telescope started to detect any faint blue specks surrounding nearby stars. If he had lived longer, he could have led and encouraged the next great advancement in human knowledge of the cosmos as an authoritative elder statesman. Instead, Sagan's Voyager and Galileo observations of Earth were perhaps the closest astronomers would get for many generations to studying a living alien world before his death, and the eventual relegation of TPF to NASA's technology development dustbin. While Sagan studied Earth from a distance in 1990, Sara Seager started her first year at the University of Toronto and quickly finished her introductory science and math courses. She had persuaded her father, a physician who quit his job to launch a small hair transplant company, that she would go into pre-medicine. He advised her to pursue a career in dermatology because it was profitable, reliable, and comparatively stress-free. Seager quickly shifted her focus to physics and astronomy, much to her father's dismay. Since she was a young child, she had been interested in the night sky. She used to wonder why the moons seemed to follow overhead wherever they went on family car rides at night. Soon after, Seager's father took her to a star party, where she could view the moon through a telescope and hear an amateur astronomer explain its orbit. When Seager was 10, she went camping in the Canadian backcountry, which profoundly broadened her perspective on the world. She emerged from her tent at night, under a clear sky, abruptly devoid of city lights. For the first time, she felt the continuum that started with the earth beneath her feet and stretched out into the infinite as she looked up at many stars above the heavens. She discovered that some privileged people actually made a living studying stars, planets, and everything else outside of Earth when she was 16 and at an open house for a university. "You can make a living doing this," Seager remembered. "It was one of the most exciting days of my life," Seager asked. "I hurried home and informed my father, he delivered the harshest lecture he had ever given, discouraging me. He said, "You possess these innate abilities, but must be self-sufficient and independent of men." Although Seeger's father valued practicality, he insisted that she think big, set goals, and see herself achieving them. He wanted me to be independent and didn't think it was a good career choice. Otherwise, success is different from what she should expect. Despite that advice, Seeger often compared her early attempt at astronomy to a meaningless, random walk, like a photon wildly bouncing around a star's raging core. She first concentrated on physics to appease her father, who said that this would increase her chances of finding work both inside and outside academia. But the more she learned, the less interest she could muster, saying, "I thought you could use equations to perfectly describe everything." After that, I found that approximations were common, so why should I suffer for the rest of my life and put in a lot of effort for something I don't like after having done so for 3 or 4 years? March 2011, Wewrick was aware that time was running out. He put together a short 3-page list of necessities that included family members' contact details, their life insurance agent, and house and car maintenance advice. The last days of sitting up, walking, talking, and moving went by like the dawns of life, mirrored in a rearview mirror. He fought every step of the way with his usual strength, but death would not wait. A hospital bed and other medical supplies, such as long tubes and beeping monitors, were brought by the home nurses. Seeger's strategic career changes to pursue TPF was marked by a final vigil held days before her next 40 Years of Exoplanets conference. At night, she recalled cuddling up beside Wewrick in his bed and conversing with him as he emerged from the mist. She muttered to him that she loved him, that he had made her life better forever, that he could relax, and that everything would be all right. She told him he had given her the confidence to take risks, to achieve her goal and change the world. Wewrick's face lit up a little. No. It would be one of their last conversations. He shook his head. You would have done that anyway. Mike Wewrick passed away quietly at their home 2 days after Seeger's 40th birthday, with Seeger by his side. Their lengthy journey together came to an end. 7 months later, I was in Seeger's office on the 17th floor, overlooking the River Charles. She was sitting in an overstuffed red chair across from me, illuminated by a ray of bright morning sunlight that came through the large windows. A chalkboard that was covered in mysterious symbols and diagrams extended from wall to wall and from floor to ceiling behind her. Measurement of alternative biosignatures that could be found on the wide range of possible habitable planets in space was the goal of Seeger's ambitious new project. She looked rested and smiled easily. I told her. Thanks. She said, her smile fading, I feel awful. I'm a little down. According to Seeger, the month after Wewrick's death had been a blur. She found a small widow support group in Concord that met periodically to share stories and talk. To spend reconstructive time with Max and Alex, she planned multiple trips. They saw NASA rocket launches in Florida, hiked in New Hampshire and Hawaii, camped in the Southwest, traveled through Europe, and visited the Smithsonian in Washington, D.C. She felt compelled to devote herself fully to her work. Beyond her children, Seeger's vision, goal, and inspiration remained TPF. After examining me closely, she stated, there are 3 ways to get there. First, I'll apply to be a principal investigator at NASA, which is the government route. The second choice is to go after it on your own. Making enough money to pay for everything on my own is the third option. For each path, she methodically developed overlapping preparations and provided a more thorough explanation. The Exoplanet Sat project, which Seeger oversaw at MIT Draper Laboratory, was at the center of her interrelated plans. With a tiny telescope, deployable solar panels, and a simplified avionics package for accurate pointing and ground communications, Exoplanet Sat was already well on its way to becoming a nanosatellite. It was a golden metal rectangular box, no bigger than a loaf of bread. It was designed to constantly search for any signs of transiting planets on a nearby sun-like star, and it had sufficient sensitivity to pick up planets that were just a little bigger than Earth. The initial Exoplanet Sat cost roughly $5 million to develop and launch, but subsequent models could be made for roughly $500,000 each, which is incredibly cheap for any hardware that would be launched into orbit. For at least a year or two, each would operate in low Earth orbit. Since nanosatellites are so small, they typically use rockets to launch larger primary payloads instead of requiring their own launch vehicles. Seeger intended to use a fleet of low-cost exoplanet sats in the future to track all of the nearest, brightest stars to find potentially habitable, transiting planets. To support nanosatellites, Seeger intended to launch the first prototype as early as 2013. The engineering and management experience Seeger would gain from the success of Exoplanet Sat would not only make her a more appealing candidate to participate in future NASA missions, but it would also serve as a launching pad for her own development of a more ambitious spacecraft. The private route, her second choice, involved raising money to build and launch a scaled-down and simplified TPF that could look for exoplanets among the 100 nearest sun-like stars. Seeger said such a telescope might be able to characterize any habitable worlds using the photometric techniques she developed early in her career, but it would need to be larger and more sophisticated to gather spectra for any of them. The second path was already well supported by Scott Gallagher, a 50-something technologist who had co-founded the financial institutions technology group at Goldman Sachs decades earlier. They had recently formed the non-profit NextEra Foundation to pursue a private planet-finding space telescope, though they were still working out the details. NextEra's goal is to map the closest stars that resemble the Sun, but neither more nor less, Seeger said. Future generations will then be able to obtain their spectra and perhaps even figure out how to get there, in case it only detects the faint blue dots. It is not common, but it is possible. The objective is to prevent having to carry out the specifics of endless trade research. We'll choose a starlight suppression technology that has developed since the inception of TPF and fully endorse it. We'll go on if it doesn't work. It would help if you were brave enough to take risks. My friends at the Space Telescope Science Institute have been talking to you. Although they endorse this course of action, it is clear that this is not their preferred tactic. This type of risk-taking is prohibited in federally funded space science, making the model of building large, complex structures inefficient. You risk your time and money as a private company. Things might become smaller, more specialized, and less costly as a result. How about the third path? I asked. Was Seeger's get-rich-quick scheme disclosed to me? She smiled. Mining asteroids is a serious matter, despite its humorous appearance. I won't be able to oversee TPF in 30 or 40 years, but at least I'll have the money to see it through to completion myself. 2 months after our conversation, a new company called Planetary Resources Inc. went public, and I was a scientific advisor to the company. The company was co-founded by Eric Anderson and Peter Diamandis, two well-known names in the emerging private spaceflight industry. Eric Schmidt and Larry Page of Google, as well as billionaire software developer and space traveler Charles Simonyi, were among its investors. Alongside Seeger, Its advisors included Hollywood filmmaker and deep ocean explorer James Cameron, as well as former U.S. Air Force Chief of Staff General T. Michael Mosley. The basic idea behind the business plan was to locate and extract valuable resources from near-Earth asteroids, many of which are thought to contain deposits of platinum and other rare metals worth trillions of dollars based on current market prices. Despite overwhelming odds, its core team stood to profit multi-billion dollars if the venture eventually succeeded. Planetary Resources planned to begin by building and deploying small space telescopes and charging the public and private sectors for observing time to remotely prospect asteroids. We deployed fleets of nimble robotic spacecraft to rendezvous with the most promising asteroids for a closer inspection and eventual recovery of their rich resources. And we set up a low-cost interplanetary communications network. We could turn water and other volatiles into rocket fuel, opening the door for the construction of orbiting fuel depots and gas stations in space to serve paying customers. The consumer market for computing devices and renewable energy could be significantly expanded by bringing platinum group metals to Earth. Additional revenue would come from third-party licensing of the interplanetary communications network and the technology for inexpensive interplanetary spacecraft. Through her work with nanosatellites, Seeger would contribute her expertise in developing small telescopes and on-orbit communications, her understanding of remote photometric and spectroscopic observations, and her access to MIT's research community. According to her, the project was part of a bigger strategy to help the Earth's economic sphere expand throughout the solar system and eventually beyond. It is frequently forgotten that space science is currently regarded as a luxury field. Unlike fighting poverty, AIDS, cancer, or global warming, people do not consider it a duty. We might have to do it on our own without government assistance, but a thriving commercial space industry can only help. Later, she showed me the more concrete, but no less futuristic portion. Her plans include the young people from the many prestigious MIT research groups she led, mentored, and oversaw. Those who traveled from Europe, Asia, and South America to work with Seeger included Diana Valencia, Renyu Hu, Bryce DeMaury, and Vlada Stamenkovic, all of whom were already regarded as rising stars in their respective fields. Becky Jensen Clem, Christopher Pong, Mary Knapp, and Matt Smith were all MIT natives, who either graduated early in their careers or were MIT undergraduates. For Seeger, each was crucial to his efforts to build spacecraft or study exoplanets. Seeger added that her young protégés are another part of the legacy, telling me, "They're almost like my extended family. They will mature, take off, and fill the world with the next generation of brilliant work in the atmospheres and interiors of exoplanets if I don't find the biosignatures. They will." We took the train back from Cambridge to Seeger's home in Concord in the evening. It was a big 3-story house with a comfortable screened-in porch and a large backyard encircled by trees. Brown-haired and barefoot, Max and Alex greeted us inside by sprawling on their bellies as they put together Legos and took notes in coloring books. Their babysitter wished us a wonderful evening after packing. From a stack of papers nearby, Seeger took out a sheet of index cards and poster boards. Over a picture of a smiling, slug-like alien with eyes on stalks, a game she had made with her children, she had handwritten Alienopoli in block letters across the poster board. Boardwalk and Park Place could be swapped out for the worlds of Alpha Centauri or the planets of the Gliese 581 system, which players could buy separately. Rolling the dice could send you into a UFO and expose you to the humiliation of alien kidnapping and quarantine, or it could send you into a wormhole and take you anywhere on the board. Seeger excused herself to make baked chicken, rice pilaf, and artichoke hearts for supper in the cornflower blue, tiled kitchen. Seeger left me with the boys, who refused to talk about their mother's work or play Alienopoly. "Do you like Star Wars?" They chirped nearly at the same time. I nodded. They exchanged intense glances. Alex padded back to shove one into my hand, after rushing to a nearby couch and removing 3 toy light bulbs from between the cushions. Despite my Sith training, the young Jedi repeatedly disemboweled, dismembered, and decapitated me in 2 45-minute bloodbaths before and after dinner. Max and Alex reluctantly trudged upstairs to their beds, long past bedtime. Seeger and I stayed downstairs and chatted over glasses of red wine while she was doing laundry. "You must protect yourself, Darth Vader," Max cried as he raised his weapon. She seemed baffled by her son's love of swashbuckling space operas, rather than the incredible reality she and her co-workers were learning about every day. "Do you know why they are so obsessed with Star Wars?" After some time, she asked. I murmured about folklore's cultural archetypes and Joseph Campbell's hero's journey, the timeless fantasy of frontiers and creatures that looked familiar but exotic. "Perhaps," she said, her face quizzical, and I said, "I don't really know what it is, why people do what they do." I thought of the stories Seeger had told me about Alex, saying he would become an astronaut to explore the Earth-like worlds his mother would find, and Max pretending to be a visitor to Earth from an alien planet. I thought back to my childhood, when I dreamed I might visit a comet or be taken away by a UFO to visit a different galaxy. Every child lives in a world full of possibilities. They dream of exploring and inhabiting different lives and worlds, thinking they are special and unique enough to do so. I couldn't say if so many dreams died at the end of childhood because of harsh realities or untapped potential. I can still make the maps, but I can't really say anything about what happens after that. Could a civilization gather resources and travel to the closest stars if it wanted to? Seeger said, "I know I'm not going to live to see people travel to an exoplanet." She took a break to change a load of laundry before returning to talk about her new work in biosignatures, adding, "I think that is within our reach." With the assistance of her collaborator, the UK-based biochemist William Baines, Seeger was constructing plausible alien worlds that were very different from Earth to measure biosignature gases and biospheres in their atmospheres. Starting from the premise that planetary life was common, despite the possibility that Earth-like planets might be rare, she and Baines sought to create a list of potential types and scenarios. She talked about anoxic slime worlds, with oceans covered in massive mats and biomass blooms that pumped out hydrogen sulfide or methane, and gas-blanketed greenhouse worlds far from their stars where life got its energy from splitting water and combining hydrogen and nitrogen to create power. Ammonia. She pictured life flourishing in the bubbling aerosols created by the fluid, turbulent interface of sea and sky, envisioning twilight blue worlds in which life could easily swim and fly between air and water, intermixed at precisely equal densities on warm ocean planets, wrapped in oppressively thick atmospheres, each of which required simulation of millions of planetary surfaces and atmospheres to determine how such things might appear in a future TPF-style telescope, each with its own set of thermodynamically plausible assumptions that would affect the production and visibility of biosignatures. As usual, some in the field thought Seeger's new research was too futuristic to be of any use, asking why it was necessary to explain biosignatures for planetary environments that might not exist and could only be observed with telescopes that might never be constructed. We will soon be able to see some of this, she said, sipping her wine. All of this work is purely to prepare us for an eventual interpretation of unclear observations. First, we will be able to see some transiting super-Earths near quiet, nearby M dwarfs, the ones with long, puffy atmospheres that the James Webb Space Telescope, and perhaps even ground-based telescopes, can probe. But that will limit our chances of finding our Earth twin, because any spacecraft we launch in our lifetimes probably can only observe the nearest 100 stars. So how can we identify biosignature gases in that space if we still rely on Earth twins for surveying? We need to do this thorough first principles analysis to do so. Our first observations of super-Earth atmospheres may humble us tremendously. She had shaped her career, I noted, by foreseeing and looking farther ahead than her contemporaries. What did she think lay ahead? What would keep the exoplanet boom going while the dream of a TPF was on hold? I posited that the field was on the verge of dot-com collapse after 2 decades of unchecked expansion. Seeger began, "At the Next 40 Years conference, this really crystallized for me. Rogue pioneers built this field," she thought, as she rolled the stem of the glass between her fingers and took a longer sip of wine. It's a selection effect. You only found yourself in this predicament because you were a risk-taker, tough and aggressive person who held yourself to a high standard. Quality control is deteriorating as more people enter the field. Nowadays, a large number of people are carrying out the same tasks with only minor modifications. The nearby stars should be mapped. We can't agree on the best course of action, even though everyone agrees. She bemoaned what she saw as a growing surplus of sloppy theoretical research and observational findings that made only minor contributions to the field. Are so many more transiting hot Jupiters really necessary? She thought. Although we don't require more, we do. That's not the best thing for me to say. However, she added, there were advantages to the need for greater unity. Exoplanets do look like a dot-com bubble, in fact, but we anticipate that this phenomenon will continue for a century. It has always been the case in astronomy that new fields are created as a result of new technologies and telescopes. We employed high-precision spectrographs and radial velocity. It's happening in Kepler and transit. To me, it looks like waves. Even though your RV wave is currently supporting, it might return in the future if Earth is present in the majority of stars. A wave is currently being created by Kepler transits. You'll have more waves later. The direct imaging wave is coming. TPF will show up. They all overlap. But because they start at different times, their phases are different. The bubble will last, because you can't have everything at once. The bubble would probably burst if we spent billions of dollars on them all at once. Since many aspects are gradually opening up, this trend will continue. People will still be working to increase the resolution of their atmospheres and surfaces, even after we have located and directly imaged a potential Earth. It won't last forever, though. She drained her wine and looked at the time. It was past 11 p.m., and I had to catch the train back to Cambridge. But before I left, she said she wanted to show me something. Max and Alex were in bed when we went upstairs, and we entered a small study with a couch and bookshelves. From a closet nearby, she pulled a few framed yellowing photographs and placed them prominently on the couch. Most of them featured Weverick looking dignified and gaunt after a long day of hiking, pulling a canoe through rushing water and bestriding a boulder on the top of a massive esker. He gazed into Seeger's eyes as they shared an embrace on their wedding day. She wore all white, and he wore a black suit jacket and tie. Others showed plumes of undulating black smoke smearing out the blue sky, above a shoreline of dead, charred trees, and others showed sunlight reflecting off mist above roaring rapids. While we were traveling, Mike would cook, and I would take pictures. Seeger remarked softly, "I used to be really into photography. I'm not attempting to. Could you focus on the death of my husband?" His passing, though, was a serious setback. It's causing a big chain reaction. These days, I'm trying to live a more purposeful life. My commitment is to my students, mentees, and kids. I'm working harder than ever to encourage people to overcome challenges and go after their dreams, mine included. The next day, I met Seeger in her office and followed her through a busy afternoon of meetings, phone calls, and classes. Every hour, Seeger's mind shifted to a new set of issues, whether it was advising postdocs on their research projects on exoplanets, talking with her graduate group about the subtleties of satellite thermal control, or giving undergraduate engineering students project management advice. I was exhausted from the evening, but Seeger seemed to have no end in sight. She asked to take the qualifying exams for a ham radio license because she was interested in communication satellites, so we split up for a few hours. After dinner, sushi was served at a restaurant on campus. Before we left, we rode the elevator back through the night to the green building because she had left a bag in her 17th floor office. The city lights glinted in the window of the dark, rippling river, and for a moment, we felt as if we were floating in deep space, looking down on a galaxy's countless glittering stars. She looked up from her desk search and paused, bag in hand, to enjoy the view. I love the skyline. It always gets me. The river turned back to face me, the sky, the light. My life is greatly impacted by the view and how it changes, how darkness creeps in. I think about how the world fits together, the continuum of light, and all the people as I gaze out. Day becomes night, and night becomes day once more. Nature sets the course, but we have some control. We don't have time to waste, even though we've been evolving for millions of years. You know, death helped me realize how useless most things are, she said, her voice faltering and breaking before regaining its strength through tears. Everything matters and takes precedence over everything else. I can't tolerate pointless things any longer. They have no time. Does that make sense? A single point-like figure in the foreground stooped beneath a red arc, and in the shadows, I suddenly remembered a framed picture she had shown me the night before. A unique photograph taken from above by Weverick that showed a vast expanse of yellow grass-stunted trees stretching to the shores of an unnamed lake, reaching the treeless horizon. The sun cast a long shadow, and Seeger pushed the heavy canoe resolutely across the hostile transition zone. The barren lands rolled on in the distance, the low-resolution image perhaps revealing whether the difficult portage was beginning or ending.